Today, we're going to start the first of a three-part episode on the Gram-Schmidt orthogonalization process and orthogonal complements. But first, let's review inner products and norms as we did in the last lesson. Let's denote V as the collection of n-dimensional tuples, and we're going to consider the case of p-norms where p is equal to 2. Recall that the length of a vector x is the following scalar, where a sub k is just the kth entry in our vector x. This is just the 2 norm of the vector x. We'll define a map angle bracket that takes two vectors x and y and returns the scalar a1 times b1 conjugate plus a2 times b2 conjugate, and so forth. This is what is known as the standard inner product on our vector space V. Given three vectors x, y, and z in our n-dimensional space and a scalar c, the inner product has the following properties. First, there is linearity. That is, the inner product of cx plus z and y is the scalar c times the inner product of x and y plus the inner product of z and y. Next, we have symmetry. That is, the complex conjugate of the inner product of x and y is just the inner product of y and x. Third, we have positivity. That is, the inner product of a vector x with itself is a non-negative real number. We have non-degeneracy. That is, the inner product of a vector x with itself is equal to 0 as a scalar if and only if x is equal to 0 as a vector. And finally, we have Lagrange's identity. This is a rather strange identity that says you can consider the product of the sums of squares, and this is also the sum of squares. But instead of thinking of it this way, really this reduces to saying that the absolute value of the inner product of x and y is less than or equal to the product of the two norms, that is the 2 norm of x times the 2 norm of y. We wish to extend this concept of a standard inner product to something for all m by n matrices. To this end, let's consider the following definition. We'll say that a map, in terms of angle bracket, is an inner product on a vector space V if the following four properties hold. That is, for any vectors x, y, and z, and any scalar c. The inner product of cx plus z and y is equal to c times the inner product of x and y plus the inner product of z and y. Second, we have symmetry. That is, the complex conjugate of the inner product of x and y is equal to the inner product of y and x. Third, we have positivity. That is, the inner product of x with itself is a non-negative real number. And finally, we have non-degeneracy. That is, the inner product of a vector x with itself is equal to 0 as a scalar, if and only if x is equal to 0 as a vector. Indeed, the difference between this slide and the previous slide is that the previous slide was a series of properties for a specific map. Here, we're using this as a definition to say if we have any map at all that we're calling here angle bracket, this will be called an inner product if these four properties are true. Well, let's show that there actually are infinitely many such examples. Again, we've seen that the standard inner product is one example of an inner product. Now, choose n positive real numbers, r sub 1, r sub 2 through r sub n, and let's consider this new map, angle prime, that's defined as follows. Our angle bracket prime of two vectors x and y will be the following sum. R sub 1 times a sub 1 times b sub 1 conjugate plus r2 times a2 times b2 conjugate, and so forth. This is an example of an inner product for any fixed positive real numbers r1 through r sub n. In particular, there are infinitely many inner products on our n-dimensional space V. Let's give another example. Now let's say that V is the collection of m by n matrices. Let's choose mn positive real numbers Rij, and let's consider the following map angle bracket on our collection of matrices. It will take two matrices A and B and return the following sum as the sum over all of the entries in row I and column J. That is, we have a sum here Rij times Aij times Bij conjugate. The statement is that this is always an inner product. We'll now make a couple of definitions. We define the adjoint of an n by n matrix as the transpose of the complex conjugate of our matrix. Whenever Rij is equal to 1 for all entries I and j, we'll call this the Frobenius inner product. That is just the sum Aij times Bij conjugate. As a remark, you'll notice that the Frobenius inner product reduces to the standard inner product when either m or n is equal to 1. Just like before, this actually shows that there are infinitely many inner products on the collection of m by n matrices. Finally, in the last lesson, we defined the concept of a norm. Again, let's say that we have an inner product, our angle bracket. Since we know that the inner product of a vector x with itself is non-negative, we'll define the norm of a vector x as just the square root of this inner product of x with itself. The main property about norms is as follows. Let's say that we do have our map double vertical bars as the norm. We have the following properties. First, we have positivity. That is, the norm of a vector x is always non-negative. Next, we have non-degeneracy. The norm of a vector x is 0 as a scalar if and only if x is 0 as a vector. Third, we have multiplicativity. That is, the norm of a scalar c times a vector x is the absolute value of this complex number c times the norm of our vector x. Fourth, we have the Cauchy-Bunyakovsky-Schwarz inequality. This says that the absolute value of an inner product of a vector x with a vector y is less than or equal to the norm of x times the norm of y. And finally, we have the triangle inequality. This states that the norm of the sum of two vectors is less than or equal to the sum of their norms. More generally, any map with the above 5 properties will be called a norm. We have the following remarks. Notice that if V has an inner product, then it has a norm. This was the content of the previous slide. However, not all norms come from inner products. Indeed, when we defined P norms, these were all examples of a norm, where P is any extended real number between 1 and infinity, but the only one that comes from an inner product is P is equal to 2. We'll say that a vector space V with a norm is a Banach space, whereas a vector space with an angle bracket, that is the inner product, will be called an inner product space. The idea of a Banach space is that it's a vector space with a norm, since we have the concatenation Banach space. And the idea of an inner product space is that it's a vector space with an inner product space. Notice that every inner product space is automatically a Banach space because we can define its norm by the square root of the inner product of a vector x with itself. However, for extended numbers p between 1 and infinity, we can define a p norm, therefore we have a Banach space. But in general, these Banach spaces are not inner product spaces. Today, we're going to introduce the concept of an orthonormal basis. Let's say that V is an n-dimensional vector space over either the real numbers or the complex numbers. We've already seen that if we have a basis beta, then our coordinate transformation, that is our standard representation, allows us to think of every element x in our vector space V as an n-tuple, our square bracket x, a1, a2 through a sub n. Since this standard representation, phi sub beta, is an isomorphism, we might as well assume that V is our n-dimensional vector space f to the n. So from here on out, we're not going to focus on arbitrary n-dimensional vector spaces. We're just going to focus on V is equal to f to the n. The reality is we like to choose our basis beta so that it has, quote, nice properties, unquote. The idea is as follows. Given a basis gamma of our space f to the n, we're going to introduce an algorithm that will construct a new basis beta, which is, quote, nice, unquote. Here's our definition of what it means to be, quote, nice, unquote. Let's fix an inner product, angle bracket. We'll say that a subset beta is an orthonormal basis if the following four properties hold. Number one, beta should span V. Number two, beta should be a linearly independent set. Number three, beta should be an orthogonal set. That is, given any two vectors vi and vj in beta that are different from each other, the inner product of vi with vj should be zero as a scalar. And third, beta should be a normalized set. That is, given any vector v sub j in beta, its norm, that is the square root of the inner product of vj with itself, should be 1. Let's give some examples of these so-called orthonormal bases. Let's say first that v is equal to f2. And let's consider our angle bracket to be the standard inner product. Recall that we have the standard basis, gamma, that just consists of the vectors e sub 1 and e sub 2, where e sub 1 is the vector 1, 0, and e sub 2 is the vector 0, 1. We've already seen that we can actually write down many other bases. Let's take a and b to be any two real numbers, not both 0, and let's define new vectors v sub 1 and v sub 2 as you see here on your screen. We claim that this set beta, consisting of these two vectors v1 and v2, is an example of an orthonormal basis. As a corollary, when a is equal to 1 and b is equal to 0, we actually recover e1 and e2. So actually, the standard basis is an example of an orthonormal basis. More generally, because a and b are really anything, we can say that there must be infinitely many orthonormal bases for our vector space F2. In order to show that our set beta really is an orthonormal basis, we have to show that four properties hold true. First, let's show that beta spans V. Given any vector in V, let's call this vector C1, C2, we can actually write this as a linear combination of our two vectors v1 and v2, where we'll pick our scalars a1 and a2 to be the numbers that you see here on your screen. Next, let's prove linear independence. That is, we'd like to ask what are all solutions to the equation a1 times v1 as a vector plus a2 times v2 as a vector equals the zero vector. This corresponds to a system of two equations, two unknowns, where we try to solve for a sub 1 and a sub 2. In working out what you see here on your screen, we can actually solve for a1 and a2 to find that they both must be 0. Hence, the only solution must be 0, so we see that our set beta must be a linearly independent set. Third, we will need to prove orthogonality. Since a and b are real numbers, we can actually work out the inner product of v1 and v2. That'll just be the sum that you see here on the screen. Remember that the sum should look like a1 times b1 conjugate plus a2 times v2 conjugate. By writing that sum here, we see that everything cancels out and we find 0. And finally, we have to say that our set beta is a normalized set. That is, the norm of every vector in our set is 1. Again, we can find this just by multiplying out the numbers in the set. We can write down a similar statement for F3. This is three-dimensional space. Again, let's choose angle bracket to be the standard inner product on our space. We have here the standard basis gamma in terms of the vectors e1, e2, and e3. Now, for any real numbers a, b, and c such that a and b are not both 0, we can write down three new vectors v1, v2, and v3 as you see here on your screen. We claim that this set, beta, formed by these three vectors, is an orthonormal basis for our three-dimensional space F3. Just like before, we see that when a is equal to 1, b is equal to 0, and c is equal to 0, that we actually have an orthonormal basis that is just the standard basis. In fact, because A, B, and C really can be anything, there must be infinitely many orthonormal bases for our vector space F3. Just like before, some matter is showing that four properties are true. First, if we'd like to show that beta spans V, we first consider any vector C1, C2, C3 in our vector space V. Now it's a matter of showing that we can actually find scalars A1, A2, and A3 that add up in the way that we'd like. But this is algebra, and you can see the result here on your screen. Next, we'd like to prove linear independence. Well, here the idea is that we have to take a look at the sum that adds up to the zero vector and ask what are all scalars A1, A2, and A3, so this is the case. Upon solving the system of three equations, three unknowns, we find that the only solution is A1 equals 0, A2 equals 0, and A3 is equal to 0. For orthogonality, this is just a matter of multiplying quantities out. For the inner product of V1 and V2, we see that our sum here just becomes 0. For the inner product of V2 and V3, again, we see that the sum here just becomes 0. And for the inner product of V1 and V3, there's a little work that we have to do here, but again, we see that the sum goes to 0. Finally, we have to show that the vectors in our set beta are normalized. Here, we just take the norm of our vector V1, and by taking the square root of the sums of the squares, we see that we find 1. Similarly, the norm of V2 also reduces to 1. And there's a little bit of work, but the norm of V3 also reduces to 1. So we do indeed have an orthonormal basis. Thanks very much for watching.